Hello everyone, and welcome to another video brought to you by RouTube. In this video, I will be covering normal distribution and Z-scores, which students will be taught in Year 12 Further Maths. 4 learning objectives in today's video, a couple of which I have taken straight from the Year 12 Further Maths study design. So the first one is to use the normal model for bell-shaped distributions and the use of the 68, 95, 99.7% rule to estimate percentages and to give meaning to the standard deviation. The second objective is to calculate Z-scores using multiple methods. The third one is to use Z-scores to compare data values across multiple distributions. And the final objective is to convert Z-scores into actual scores using the relevant formula. Okay, so let's begin having a look at normal distribution and understanding what it is and what it looks like. So many data sets are roughly symmetrical and have approximate bell shapes, as can be seen in the histogram below. Data that contains a bell shape, so if you do get data or a graph that does contain a bell shape, it's often referred to as being normally distributed. Okay, and the reason why I've highlighted that is because normally distributed is a really common term that's obviously used in Year 12 Further Maths, but that's the terminology that often gets used in SACs and in exams. Okay, so it's really important, as soon as you see normally distributed, you should understand what that means. So as soon as you see the terminology or the term normally distributed, you should be able to apply the knowledge of normal distribution and the percentage rule, which we'll get to in the next part of the video. So normally distributed is a really important term that you need to know because it will pop up multiple times throughout the year in SACs, practice exams, and at the end of year exams. So data which is normally distributed have their symmetrical bell-shaped distribution centered on the mean value, which is x bar. Okay, so when we're talking about normal distribution, everything is always in reference to the mean. Okay, the mean value, which is x bar. Now, also what often gets forgotten is that when we're looking at normally distributed data, it's really important to note or to remember that the mean is equal to the median, or the mean and the median are approximately the same or approximately equal. Okay, so that, like I said before, that often gets missed and has popped up a couple of times in exam questions and has tricked a couple of students. So it's really important when you have data that is normally distributed, which we're going to explore today, the mean and the median are approximately equal. All right, so let's now be introduced to the 68, 95, 99.7% rule. Now, before we get into this rule, I think it's really important to understand that or hopefully you've got a base understanding of the interquartile range and standard deviation. So for those that don't, the interquartile range, or IQR as it's often referred to, is the measure of spread of a data distribution around the median. Okay, so that's the interquartile range. So that's something that you already need to know that we're not going to look at today or in today's video, but that's something that you'll definitely need to know for this year. But what we are going to look at today, and what you do need to know when we're looking at the percentage rule and the normal distribution, is the term of standard deviation. Okay, so the standard deviation is what we use to measure the spread of data distribution around the mean. Okay, so the interquartile range is around the median, whereas the standard deviation is all in relation to the mean. Okay, and hopefully you'll be able to get a really good understanding of the standard deviation around the mean from today's video. So let's get into it. So the 68, 95, and 99.7% rule for a bell-shaped curve states that approximately, okay, so 68% of data lies within one standard deviation either side of the mean. Okay, so if we have a look at our bell curve here, and a lot of times when we look at something graphically, it's a little bit easier to understand. Okay, so we always start from our reference point, which is, I've just highlighted in yellow, which is our mean. Okay, our mean, remember, normal distribution, it's always about the mean. Okay, so we always have a reference point, which is the mean, which is smack bang right in the middle. So then if we have a look one step to the right and one step to the left, which I will color in blue. So we've got one step to the right and one step to the left. Okay, so you'll see x bar plus s to the right and then x bar minus s. What that means is it's just one standard deviation. So it's x bar, which is the mean, plus one standard deviation above, and then x bar, which is the mean, minus one standard deviation. Okay, so what it says is that totaling 34% and 34%. So approximately 68%, because we add those two values together, 68% of the data lies within one standard deviation of the mean. Now, if we keep moving along, now we'll go in green. So we keep moving along, and now we have X bar plus 2 standard deviation, and now X bar minus 2 standard deviation, either side of the mean. So now we've got our 68%, and then we're going to add these two values. So we've got 68% plus 27, because 13.5 and 13.5 is 27. So therefore, 68 and 27 makes 95%. So what it says is that 95% of the data lies within 2 standard deviations either side of the mean, either above or below the mean. And then finishing off, let's go with orange. So now we've got 99.7. So if we have a look here, we've got now X bar plus 3 standard deviations, and then X bar, which is the mean, minus 3 standard deviations. Okay, so what that means is now we add those percentages, and the only thing we've got above is 0.15% and below is 0.15%, okay, which totals 0.3. So we subtract that from 100%, which then leaves us with 99.7%, and I'll highlight that in orange. 99.7% of the data lies within 3 standard deviations either side of the mean. So as you move up or down by standard deviation, okay, you obviously cover more of your data. Okay, so 68% of your data lies within 1 standard deviation, 95% of your data lies within 2 standard deviations, and 99.7% of your data will lie within 3 standard deviation either side of your mean. All right, let's have a look at answering a question using the 68, 95, 99.7% rule to estimate some percentages. So let's have a go at this question. A certain variety of pine tree is normally distributed. Okay, there's the terminology as I was saying about before. That's the terminology you'll be definitely challenged with and asked in, or probably in SACs and definitely in exams. Okay, and you'll most probably see them in practice exams as you progress through the year as well. So as soon as you see that terminology, normally distributed, you know you need to go to your reference, have a look at your summary notes, and go straight to the bell curve and apply your knowledge on the 68, 95, 99.7% rule. Now, so a certain variety of pine tree is normally distributed and has a mean trunk diameter of 120. Okay, so there's our mean, and a standard deviation of 25 centimeters. Okay, so important to highlight the important information. And approximately what percentage of these trees have a diameter greater than 145 centimeters? Okay, so we've got plenty of stuff to do. Now, remember I said before, everything is always centered around or about the mean. Okay, so our starting point or our reference always has to be the mean to begin with. So if I'll just circle it in the question, your mean is 120 centimeters. So what you need to do is when you've got this, so the bell curve drawn up, now my recommendation is you don't need to draw it every question, okay? Just have one in your reference notes and you can just sort of fill it out as you go each time, okay? Rather than needing to draw it up and putting the percentages as you go. So we're going to first input our mean, which is 120. Remember, that's always the position of the mean. And then now let's move up 1 standard deviation. Okay, so we're going to go right, which is moving up 1 standard deviation, and the standard deviation is increasing and decreasing by 25, which I've just circled in the question. And let's start filling out our values. So 120 plus 25 gives 145. Then 145 plus 25 gives us 170. And then one last one to get to X bar plus 3 standard deviations. So 170 plus 25 gives us 195. And then now I'll just change color and we're going to go backwards now. Okay, so we're going to decrease by 25 now. So we've got 120 and then we're going to decrease by 25, which should be 95. And then again, decrease by 25 to give us 70. And then again, decrease by 25 to give us 45. Now, once you have this filled out, any question that you get asked should hopefully be a lot easier once you have this filled out. okay, just like we've done. So the important thing is fill it out first, just like I've done, and then any question you'll be asked, you should be able to fill out, you should be able to complete, and you should hopefully not have too many issues with. Okay, so let's go back to the question. So approximately what percentage of the trees have a diameter greater, and I'll circle that in red, greater than 145? Okay, so what we need to do is first of all locate 145, which hopefully you'll identify, I've just drawn it in blue, is 1 standard deviation above the mean. Okay, so it's 1 standard deviation above the mean, which is easy to find now because we have filled it out. Okay, now we need to work out what percentage is greater. So we're going to look for all the percentages to the right because they are greater than. Anything to the left is less than. All right, so all these percentages. So we're going to have 13.5%, 2.35%, and 0.15%. Okay, so let's add those up. So here we have 13.5, and then we're going to add 2.35, and then we're going to add 0.15. Okay, and then hopefully if you add it up correctly, you should end up with an answer that is 16%. Make sure you don't forget the percentage sign because the question is asking you for a percent or a percentage. Okay, so here we can clearly say that 16% or approximately 16% of those trees have a diameter that is greater than 145 centimeters. Okay, now even if you were asked less than or greater than a different value, you should still be able to answer the question once you have it filled out with the mean and with the increase and decrease by the standard deviation. So do that first as we did, and then like I said, hopefully you won't be too tripped up on any question that you might be asked. All right, let's have another go at using the 68, 95, 99.7% rule, but this time we're going to be asked a slightly different question. Okay, so let's have a look. When a sample of matches in a box was studied, it was found that the number of matches in a box was normally distributed. Okay, there we go. Once again, it comes up in the wording. Okay, it was normally distributed with a mean number of matches of 50 and a standard deviation of 2. Okay, so we are given everything we need. Okay, so again, as long as you have reference to the bell curve and the percentages and the increase and decrease by the standard deviation around the mean, again, hopefully won't encounter too many issues with a question like this either. And let's keep reading. In a sample of 200 boxes, how many, okay, so how many would be expected to have more than 48 matches? Okay, so now hopefully you'll see the difference between this question and the question previously. Last question we were looking for the percentage, whereas this time we are looking for the number of. Okay, so our answer shouldn't be in percentages. And often when we look at examiner reports, that's a really common error that occurs. A lot of students either write percentages when they're supposed to write a number, or number when they're supposed to write percentages. Okay, so it's really important to highlight, underline, or circle the command in the question which is asking you or telling you what you actually need to do. Okay, so if we remember previously, everything's always centered around the mean. So let's input our mean first. So with a mean number of 50 matches. Okay, so we're going to begin with our mean of 50 and a standard deviation of 2. Okay, which means we increase and decrease by 2. So let's increase first. All right, so 50 plus 2 is 52. Then we've got 54 and 56. And then we're going down. We've got 48, 46, and 44. Okay, as always, fill that out first. Okay, now, in a sample of 200 boxes, how many would be expected to have more than 48? Okay, so again, let's identify where 48. 48 is, hopefully you can see, is 1 standard deviation below the mean. It's to the left of the mean. Okay, so your 48 is here. I've just colored it in blue. So now we want to know how many matches would be expected to have more than 48. So we want to work out all those values to the right. Okay, so we're going to circle the percentages that we need to add up. Okay, so if we add up all those percentages, well, there's two ways you can do this. You can either add up the percentages on the left and then subtract it from 100, or you can just add up those circled percentages, which we've done now, which is 34 plus 34 plus 13.5 plus 2.35 plus 0.15. Okay, now you don't need to do this every time. I'm just sort of stepping it out for you. Okay, and hopefully you get an answer that is 84%. Now, it's really important. That would be a common error if we stopped there. Okay, because it's not asking you for the percentage. It's asking you for, and I'll circle it, how many. Okay, so we know that 84% of them will be expected to have more than 84 matches. Sorry, more than 48 matches. Okay, that's what we just found out. But we want to know what number that equates to. We don't want to know the percentage. So what we need to do now is we need to work out 84% of the sample that we're talking about, which in the question, and I'll circle it again, was 200. All right, so we want to work out 84% of 200, which you can just put into your calculator as either 84% with the percentage sign, or you can put it in as 0.84 multiplied by 200, and then hopefully you get an answer of 168. Okay, so that's our answer. 168 boxes will be or would be expected to have more than 48 matches. Okay, so please make sure you don't stop at the percentage. It's really important that you understand whether you're asked for the percentage or whether you're asked for the number of. These are two questions that are really common when dealing with the 68, 95, 99.7% rule. Read the question and answer really, really carefully. All right, now we're going to get an introduction into Z-scores, and Z-scores and normal distribution tie in really well together, which is why I thought to create a video combining both. So Z-scores, what are they? Okay, so Z-scores are also known as standardized scores or a standardized score. Okay, so it's really important that you understand whether you're asked for a standardized score or a standard score or a Z-score. Okay, they all mean the same thing. Now, what do? Well, they allow us to compare scores in a particular distribution or in multiple different distributions. Okay, now what do? They measure the distance from the mean in terms of the standard deviation. Okay, so again, we're dealing with the mean and the standard deviation, which we have been doing for a few minutes now. So a negative Z-score indicates that the score is below the mean. Okay, so if we can have a look down the bottom here, I've just got in blue the Z-score. Okay, so what it means is if you've got a Z-score that is negative, like we've just read, it's below the mean. Okay, so if you've got a Z-score of -1, it means that that specific score is 1 standard deviation below the mean. If you've got a Z-score of -2, it means that that score is 2 standard deviations below the mean, and so on. Okay, if you've got a Z-score of 0, as we can see down the bottom, 0 indicates, if you get a Z-score of 0 or a standard score of 0, it indicates that the score is equal or the same as the mean. And then if you get a positive Z-score or positive standard score, that indicates that the score is above the mean. Okay, so if you get a positive score, so a Z-score of +1, it means it's 1 standard deviation above the mean, or if it's 2, then it's 2 standard deviations above the mean, and if the Z-score is +3, then it is 3 standard deviations above the mean. Now, it's really important, Z-scores can be decimals, okay, so they are not always whole numbers, as you can see here. So for example, if you get a Z-score of 1.5, it just means that it's 1.5 standard deviations above the mean. And then if you get a -2.6, it means it's then below the mean, or 2.6 standard deviations below the mean. Okay, so the same idea, but it can be whole numbers as well as decimals. All right, let's have a go at calculating Z-scores. Okay, so to calculate a Z-scores, we use the formula. So Z is equal to X minus X bar over S. Okay, so X is the score or the actual score, the score that we are talking about to find out whether it's got a positive or a negative Z-score or a 0. X bar, as we know, is the mean, and S is the standard deviation, which we are hopefully familiar with by now. Okay, so that's a specific formula in which we use to calculate z-scores. Okay, and you'll see the bell curve on the right. We're going to have a look how we can calculate z-scores in multiple ways. Okay, so let's have a go at the first way first. So in an IQ test, the mean IQ is 100. Okay, in an IQ test, the mean IQ is 100 and the standard deviation is 13. Frank's test score gives an IQ of 126. Calculate this as a z-score. Okay, now we're going to put the normal distribution bell curve on the right. We're going to forget that's there and we're going to use the formula to work out the z-score. Okay, so we've got our formula written there, and now let's substitute the values into that formula. So we've got z equals, now x is the specific score that we are talking about or that we are given, okay, and in this case it is 126. Okay, so we want to see, is 126 above or below the mean, and let's give it a z-score. Okay, we know it's above the mean because 126 is bigger than 100, but we're going to try and work out or calculate it as a z-score. Okay, so therefore we've got 126, and then we're going to subtract the mean, which we were given, which is 100, and then we're going to put it all over the standard deviation, which is 13. Okay, now if you just put that straight in your calculator, it should give you the answer, but doing it step by step should be 26 over 13, which means that the z-score is 2, which is positive. Okay, so that means that Frank's score was 2 standard deviations above the mean. So he performed better than the mean. If you want to put a positive sign there, you can put a positive sign there. Now, let's have a look at what it looks like graphically. Okay, so let's do the same question, but on the bell curve on the normal distribution using the percentage rule. Okay, so the mean IQ is 100. Remember, we always start with the mean as 100, and then we're moving up and down by the standard deviation. So therefore, 100, we move up by 13, then we move up by 13 again, then we move up by 13 again. And then we go down by 13, which gives us 87, 74, and 61. So then now, all we need to do is locate Frank's score, which is 126, which is, I've colored in blue on the right, okay? And we can hopefully see that that is 2 standard deviations to the right of the mean, which means that the z-score is equal to 2, okay? Which you'll get the same answer both ways. So you've got your formula that you can use, and you've also got the percentage rule, which you can use to calculate percentages, values, and you can actually use it to calculate z-scores. Okay, so there's heaps of things we can do with the percentage rule. Now remember, the z-score just tells you how, or just tells you the relation in terms of the standard deviation. So if it's a positive z-score, it means it's above the mean. If it's a negative z-score, it's below the mean. And if the z-score is 0, it means that the actual score is equal to or the same as the mean. All right, let's have a look at comparing data using z-scores over multiple distributions. Okay, so Gianni scored 75 in his physics exam. So he got a result of 75 in his physics exam and 70 in his chemistry exam. In physics, the mean score was 65 and the standard deviation was 10. While in chemistry, the mean was 60 and the standard deviation was 5. Okay, really important. Highlight not valuable bits, but the important bits of the question, and we'll come back to them as we need them. So part A says write both results as a standardized score or a z-score, and then part B says which is the better result and explain or justify your answer. So simplistically, we might be able to look at this and say, well, Gianni scored 75 in his physics exam and 70 in his chem exam, so therefore his physics exam is better. Okay, but that's not necessarily the case. Okay, it's really important that, remember, the z-score tells you the comparison between the result, the actual result, around the mean. Okay, so essentially what we're doing is we are seeing how well Gianni did in relation or relative to his classmates in each specific subject or in each specific exam. So what we're going to do, we're going to split it up and let's work out the z-score. Let's do part A first. So we're going to work out the z-score. Let's not worry about the percentage distribution on the right. We'll worry about that in a second. So first one we're going to do is physics. Let's work out the z-score for physics. All right, so we've got our formula. And what we can do now, we can substitute the values into the formula. So Gianni's actual score, in physics was 75. And we're going to subtract the mean, which was 65. And we're going to divide it all by the standard deviation, which was 10. Okay, so we can pop that straight into the calculator and we should get an answer. It's going to be 10 over 10, which the z-score is +1, which you don't need to write the positive. The z-score is just 1. So that means that Gianni's score was 1 standard deviation above the mean. So he performed better or above the mean, which is awesome. Well done, Gianni. Now, let's work out his chemistry z-score. Again, we've got our formula. So now what was the actual score in, now this is, we're doing part A, so let's label that as part A. So we're now doing what's the actual score, or what did Gianni achieve in chemistry in the exam? Well, he scored 70, and we're going to subtract the average or the mean, the x bar, which in chemistry was 60, and divide it all by the standard deviation, which was 5. Again, put it straight into your calculator, and we should get 10 over 5, which will give him a z-score of +2. Again, you don't need to write the positive. Okay, so there is part A completed. So we've got a z-score for physics and a z-score for chemistry. Now, let's answer part B just down here. So which is the better result? Again, like I said before, please don't just look at the results and say, well, 75 is better than 70, so therefore he performed better in physics. No, that's not the case. It's always in relation to the mean, or in relation to, or in relative to his classmates in the specific subject. So essentially what we can do now is we can essentially see which z-score is higher. So, and let's bring in our percentage normal distribution curve below the bell curve. Okay, so 2 standard deviations is just over here. And 1 standard deviation is, I'll highlight it in a different color, is here. So that means that for physics being 1 standard deviation above the mean, that means that Gianni performed for physics in the top 16, because we've got 13.5 plus 2.35 plus 0.15%. So Gianni performed in the top 16% for physics, which is great, which is fantastic. So he performed in the top 16%. But let's have a look at his result for chemistry. So chemistry is 2 standard deviations above the mean, which means that he performed in the top 2.35 plus 0.15. So Gianni actually performed in the top 2.5% of his class, as opposed to in the top 16% in physics. So therefore, he performed higher or better, or the result that's better is his chemistry result. Now let's come up with some answer to explain why, or what proves that his result in chemistry was better than his result in physics. And there we have it. Okay, so Gianni's chemistry result was better as it placed him in the top 2.5% of his class, as opposed to his physics result, which placed him in the top 16% of his class. So like I said before, just because the physics exam result was higher doesn't mean that that result is actually better in comparison or in relation to the rest of the class. Okay, so we can see chemistry has a higher z-score, which indicates, in this case, that Gianni placed himself in the top 2.5%, as opposed to being in the top 16%, which is a z-score of 1 for physics. Okay, let's have a go at converting z-scores into actual scores. So we've looked at once we have an actual score, obtaining the z-score, but now we need to look at doing it the other way. So once we have a z-score, how do we actually calculate the actual score? So you will also need to be able to convert a standardized, which is a z-score, back into an actual score. The rule below will be applied to calculate the actual score if you already have the z-score. So its actual score equals the mean plus the standard score or the z-score multiplied by the standard deviation. Okay, so there's nothing brand new there. It's just sort of a bit of a change in the formula. Okay, so let's have a look at Gianni again. So a class test, which is out of 50, has a mean mark of 34 and a standard deviation of 4. Gianni's standardized test mark was negative 1.5. What was Gianni's actual mark? Okay, so we can see that Gianni performed below the class's average or the class mean by 1.5 standard deviations, okay, which is indicated by the z-score, which is negative 1.5. Okay, but we need to work out what or how many out of 50, how many did Gianni actually get right? So we're trying to work out his actual mark or his actual grade. So what we're going to do, the first thing we're going to do, write down what we know. Okay, so what we know first of all is that the x bar, which is the mean, is 34. Okay, we know that the standard deviation is equal to 4. And then we know that the z-score, the standard score, is negative 1.5. Okay, now we can use the formula that we've got above to then work out Gianni's actual score. So we've got x equals x bar, which is the mean, plus z multiplied by the standard deviation, right? And let's substitute the values in now. So we've now got 34. Now we're going to add a negative number, so we can just put it around brackets. But if you've got a calculator, which you should have no issues doing that. And then multiply by the standard deviation, which is 4. Okay, put that straight into the calculator, should give you an answer of 28. So that means that, therefore, Gianni's actual mark was 28. Okay, so we've now converted from a z-score into an actual score, which, like I said before, you'll need to know how to do both. So calculating the z-score, then once you have the z-score, work your way back to then calculate what his actual mark was, or what the actual mark was. Thanks so much for taking the time to watch another video brought to you by RouTube. I hope you learned a thing or two about normal distribution, the 68, 95, 99.7 rule, and z-scores. As always, please feel free to subscribe to my YouTube channel, as I will be continually uploading more maths content from year 7 to 12.